Say I was gonna join a gym. Now let's say you were gonna join a gym. And this is number 37, by the way. So you're gonna join a gym, and you're trying to decide which one you want to join. And here's Gym A. Gym A will charge you right up front just for looking at them, and they're gonna charge you $121 right off the bat. But they're really cheap after that. Every day after that, who pays daily for a gym? But every day, um, then you're gonna pay $1 per day, right? That's like how much money you're gonna spend after so many days. Gym B doesn't charge you anything to start with. They charge you $0 to start with, and then they're gonna charge you $12 a day. My word. Uh, and the kind of the question that would come to your head is, which gym should you join? Which would be better? Uh, so think about that for a second. Which gym would be better to join? And if you think about it, this one costs a lot to start with, but then it's cheaper than this one. It's cheaper per day. But this one doesn't cost anything, but then it's more expensive per day. So it kind of depends, doesn't it? If you're gonna join for like 2 days, then probably you want to go here. That'd be $24, whereas this would be $123 for 2 days. Um, but then what if you keep going for a long time? Eventually, paying $12 a day is gonna catch up to this one. This one's gonna go up not very fast, and this one's gonna come right up real fast and catch up. So in this section, um, we visualize that catching up by graphing. So in order to graph this, we first need to write some equations. I suppose that's a lie. You don't have to write equations, but we're going to, because it's good practice. Also for when things get a little more complicated. Um, so what do we have here? We have a starting amount, and then every day you pay $1. Every day you move on, you pay $1 more, and so every day your price goes up by $1. That sounds like slope to me. That's what I'm trying to get at. So why my cost? How much it's going to cost me after so many days? Well, I'm going to pay $1 a day, $1 per every day, plus I'm just going to start out by paying $121. That's Gym A. How about let's say that's for Gym A, and this is for Gym B. This is a very common notation, putting little what we call subscripts down there. For this one, you're going to pay $12 every day, but you're not going to pay anything up front. You're just going to start out at $0, right? So let's graph this first one. It seems like the better deal per day, but it's so much money up front. So let's say that this is 121, and then it's going to go. If that's 121, then $1 is not very far. So let's say it goes like this. We're just gonna follow our slope. Okay, so every day it goes up by $1. Let's say that's a day. Now with this other one, we're gonna pay $12 every day, so it's gonna go up 12 times as much. So it's gonna go up to right there the next day. And we can see after one day, this is costing a lot of money. After 2 days, this one's costing still lots of money, but you can see how this guy here, after a while, is going to catch up to this cost. And right here, on that day, you're going to, basically, whether you joined Gym A or Gym B, you are going to have paid the exact same amount. And let's see, in order to really graph this one, So this graph, this rudimentary graph, not accurate. It gives you, excuse me. Okay, so this gives you the idea that while this costs a lot up front, after that it's smooth sailing. It's not too much money. This one is zero to start with, but it costs so much that eventually you're going to catch up. So it kind of depends if you want to be a short-term member, if you just want to be there 24/7 for a while and just get really super ripped and then quit. Then maybe you should join this gym because it would cost less. But if you wanted to be a long-time member and really go for that nice tone, then you would stay with this gym for a longer time, and this would really be cheaper in the long run. And that's what we talk about, what's cheaper in the long run. So then how do we find this out exactly? Well, for this problem, since it's on such a large scale, we could just start taking some guesses. This is just to get an idea. We'll get more accurate ways of doing this later. Right, so how about for gym A and for gym B, we look at how many days you have belonged to the gym and see how much it costs for each. Let's start with 5 days. So if I join gym A, I'll have spent $5 plus 121. That's going to be $126. And for gym B, I'll have spent $60. 12 times 5. Okay, let's try like 8. So for this one, I'll spend 121 plus $8, so $129. And this one, I'll have spent $96. This one's barely going anywhere, and this one is just flying up to the moon there in price. Let's try 10. I'll have spent $10 plus my original 121. That'll be 131. This guy's going to be 120. They're catching up. Oh, this guy's catching up. Let's try 11. This will be 11 plus my 121. That'll be $132. And this one times 11 will be $132. So after 11 days, you've paid the same amount. So where you thought you might be spending less here, you might be saving some money, you actually wind up spending more. After 11 days, you're paying more with Plan B, with Gym B. So, buyer beware. And that's just to get an idea. These are the kinds of situations we can solve with what's called systems of equations. Right? We used to have one equation, now we have systems of equations that work together and have some solution. Okay? So let's look for that previous example. Here is one equation, and here's another equation. Together they are a system of equations. And when I put in 11, then for both of them I got out 132. So this 11 and 132, I can put 11 here and get 132 out here in this equation. I'll put 11 in here and get out 132 in this equation also, right? So this was a solution for this equation. At the same time, it was a solution for this equation. So this is an example of a solution to the system. Right? There you go. And in this section, we're going to start out with graphing them because we like to see pictures. We've always liked pictures ever since childhood. So number 3, just start at the beginning. It's a very good place to start. So here are two equations of lines we recognize, linear equations. And so here's what we'll do. We will graph these. And we'll graph them fairly nicely. And it says to estimate, right? To estimate. So this one's gonna, let's start with this one. So y-intercept is 2. So let's let's not be terrible. Let's graph pretty well. I go down 3, 1, 2, 3, and over 1, and there we have our line. That's pretty nice. And no one's here to tell me any different. This one, intercept of -3, right there, and up to and over 1. Oh my goodness, look at that. Right there looks like at 1, comma -1, looks like the solution. Looks like this point, remember, that any point on this line, if you take that x and that y and put it into, since this was the first equation, put it into this equation, it will make this true, right? This side will be exactly the same as this side. Any point on this line, that x and that y from, say, here or here or here or here, any of those x, y's you choose will make this equation true. This very special point right here will make this one true and this one true. It works for both. It's a solution to the system. Now let's just double check. If I put a 1 in here, then I'll get -3 times 1, that's -3. 2 minus 3 is indeed -1. Let's try it over here. 1, that's 2 times 1 is 2, minus 3 is, yes, -1. So absolutely we have found it. Okay, don't forget about that solution. What a solution is. It's this x and this y that you plug into an equation, it makes the equation true. Okay. Let's try another. Number 11. Let's jump way down to 11. X minus 7y equals 6, and -3x. Where am I? Like -3x plus 21y is equal to 12. No, is equal to -18. What do we want to do? We're going to graph these. So what do we want to do in order to graph these? Well, we probably want to put them both in slope-intercept form, right? So let's color code this stuff a little bit. Let's work in purple for this one. Let's get y by itself. So we'll get -7y is equal to -x plus 6. And let's see. Let's divide by -7. Y equals a positive 1/7 x minus 6 over 7. Okay, so in a minute we'll graph that. Now let's take this one and we'll work it out in yellow. Let's work it out over here. And so we'll add 3x to both sides. So 21y is equal to 3x minus 18. And divide both sides by 21. So y is equal to 3 over 21x minus 18 over 21. Y is equal to, this will simplify to 1 over 7x minus, this will simplify to, 3 goes into both of them, so 6 over 7. Well, look at that. This is exactly the same as this. So what's going to happen if I graph both of these on the same plane? Well, I'm going to graph this one at 6/7. So here's -1, so just slightly before -1, and then go up 1 and over 1, 2, 3, 4, 5, 6, 7, and then connect the dots. And then this one, I'm going to do the same thing. Go to -6/7, up 1 and over 7, connect the dots. So, how am I supposed to interpret this? Remember from our last example that where the lines cross, that told us, remember that all points on this line were solutions to this equation. All points on this line were solutions to this equation. And the one point that was on both lines was the solution to both of the equations at the same time. Well, look here. If I pick a point on this, I'm pointing at the purple line right now. If I pick a point on this purple line, it's going to make this equation true, and therefore this equation, because they're the same. So if I pick a point on that purple line, it's going to make this purple equation true. Any point on the purple line. Well, any point on the purple line is also a point on the yellow line. So that point on the purple line is a point on the yellow line, and therefore it will work in the yellow equation. So it will, any point on either of these lines, which are really the same line, will make both of the equations true. So how many solutions do we have? Well, we have as many as we please. We have infinitely many. As many as we want here and here, 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 here. They are right on top of each other, not just one point of intersection, like say that. Like there's a point of intersection. Everywhere they're intersecting. So they have an infinite number of solutions. Okay. Let's say number 14. 7x plus, let's not do 14. It's kind of more of the same. Let's get to a new kind of a thing. Okay. How about that? Okay, let's go to 17. Y equals -1, and 3x plus y equals 5. Okay, let's think about, we're going to graph these, so we probably want this in slope-intercept form, so let's just do that quickly. Y equals -3x plus 5. So I've rewritten this. Let's just kind of ignore this. I've taken this and written it this way. Okay, so y equals -1. Remember, that's a horizontal line. At -1, y is equal to -1. It's exactly what I'm indicating here with this line. Y is equal to -1. This is the x-axis, and this is the y-axis. So there's our line. How about this one? Okay, up 5. 1, 2, 4, 5. Down 3. 1, 2, 3, and to the right 1. Yeah, alright. There you go. And it says that at once. It says solve the system. Okay, first we're solving the system. So there's this point right here. Gotta kind of get an idea. It looks like it's probably at 2 and definitely at -1. I think this point is 2, -1. You can see why graphing is not the best and why we're going to want better ways of finding these solutions, especially when we wind up getting decimals as answers. So it looks like 2, -1. All I need to do is test it. Okay, so I take this, there's only a y in this equation. I take -1 from here. -1 equals -1, check, good. Let's see if this works with 2 for x. 3 times 2, actually -3 times 2 is -6 plus 5, that is -1. So it does work. This is the solution. Okay. Now it says to classify the system as consistent and independent, consistent and dependent, or inconsistent. So let me go back to our first problem and tell you that this problem, where we found one solution, a singular solution, because we did find a solution, we call it consistent. Consistent means there's at least one solution. Okay. And then, is it dependent or is it independent? Well, because we found one solution, actually I should go the other way around, I think. Let's put, we've got consistent on this side, and so we'll have the other jargon that goes with it on that side. We call it independent because we found one solution. And the thing that kind of helps me remember why this is called independent is because each line is its own line. They are independent of each other. They live their own lives and have families and that kind of thing, and they just meet up this one time, and but otherwise they are their own people. Okay, they might have something in common, but they march to their own drummer. But here, this one here, remember I said that we found a solution, some solution, at least one solution, and that was consistent. So this one too is also consistent because we found a solution. But this one, you see how these guys were not independent. They did not make their very own lines. They were exactly the same, right? They do the same thing, they drive the same car, they drink the same soda, they work at the same job. They are not independent, so they are dependent. They're always checking on each other. What do you have as a solution? Oh, I have that solution too. So they're kind of lame, right? It's kind of a lame. No, it's not lame. But that's what we call consistent and dependent. This one is exactly like the one we did number 3. This is consistent. Why? Because we found a solution. And it's independent. Why? Because we found only one solution. Independent. I did it. Okay. Let's look at another one. Number 28. Okay, so if you need help remembering those vocab terms, just keep going over what I just went over up there. Minus y equals -4. There's one of the equations. Here's another one. 5x minus 2y equals 1/4. Okay. Again, let's break these into colors so it's easy to follow. We'll make that one red. We'll write it in slope-intercept form. Voila. So, let's see. I want to make sure I have this right. I do not have this right. Everything else is right, but for some reason I wrote the number 2 up here. Or 8, and I should have written 2. 5/2. Oops. Okay, we're going to get on the way here. So we're going to move 5/2 x to the other side. -y is equal to -5/2 x minus 4 divided by -1. 1 equals 5/2 x plus 4. Excellent, wonderful. And blue. Let's work this one in blue. Alright, and so we'll work the blue one over here for no particular reason. -2y equals -5x plus 1/4. And we'll divide by a -2, so y is equal to, now 5 divided by -2 is going to be positive, 5/2, times x, and then divide 1/4 by a -2, you get a -1/8. Okay, let's graph these guys. Why not? Alright, so y-intercept of 1, 2, 3, 4. Go up 5, 1, 2, 3, 4, 5, and over 2. There's our slope. And aha. How about this one? It goes down 1/8. That's an interesting one. That's like a teeny little y-intercept there. It goes up 1, 2, 3, 4, 5, and over 1, 2. Right about there. Okay, and this one goes, oh, I missed it. Like, sorry, this is so sloppy. Now look at these two lines. Does it look like, well, they definitely don't intersect here. Let's ask, are they ever going to intersect? Well, take a look at their slopes. Here's, oh, I should have really done this one in blue. Okay. The slope for this one is 5/2. The slope for this one is 5/2. What do we know about slopes that are identical? If you have identical slopes, the lines are going to be parallel. The definition, well, one pseudo-definition of parallel is that they never touch. There's never a place where these two will intersect, and we know if we want a solution, then one of the solutions needs to land on both of these lines, and if they can't intersect, they can't have the same solution, and so this doesn't have a solution. There is no point that is on both lines. So this is what we call inconsistent. And enough said. Dependent, independent, it doesn't matter. There's no solution, and therefore it's inconsistent. That's what inconsistent means. It means that there's no solution. Okay? So, you should take away the idea of graphing systems, and that the intersection of those lines is a solution to both systems, and you should not lose sight of the fact that any point on a line is a solution to the equation that it came from. And that's why when you find a point that's on both of the lines, like this one, this point's on both of the lines, it's a solution to both, and therefore a solution to what we call the system. And then you have the notion of a consistent system, I'm going to abbreviate system, and that means that there is at least one solution. Okay, and consistent systems can be independent. That would be if you find one solution only. Yeah, we should put only there. And then there's dependent, where you have the same line, two of the same line right on top of each other, and they have all the same solutions. So you have infinite solutions. And then you just have plain old inconsistent systems, and that means there's no solution. Okay, and we'll learn better systems or ways of solving systems than just graphing later. But that's it for now.